Hello everybody, my name is Salma Torres and I am studying a Master of Science in Chemical Engineering at Instituto Tecnológico de Ciudad Madero. Today I will present the project Synthesis of Catalytic Iron and Nickel Phosphide Nanoparticles to obtain value-added products from the acid hydrolysis of sargassum. Since many years ago, petroleum is the most important natural resource. It is used for the massive manufacture of different products around the world. As a consequence, large amounts of environmental pollution are generated. The scientific community has paid attention to the use of biomass, since it is abundant in nature and is a natural source of carbon. Sargassum is part of the lignocellulosic biomass and currently it is an environmental and economic problem on the Caribbean Mexican coast. Sargassum harnessing represents important opportunities to obtain different value-added products through different chemical reactions. On the other hand, the use of nanoparticles as catalysts is interesting thanks to high contact area. Particularly, the phosphides present Lewis and Bronsted acidity, which promotes the acid hydrolysis reaction, facilitating the transformation of the polysaccharides present in sargassum into value. This is a nanoparticle synthesis diagram. For first, iron or nickel acetylacetonate, triphenylphosphine, oleamine, and oleic acid were mixed. The solution was heated at 200 degrees for 1 hour. In the second heating stage, the time for iron phosphate was a half hour and for nickel phosphate 2 hours, both of them at 270 degrees. Finally, nanoparticles were purified with acetone and chloroform. The Fourier transform infrared spectroscopy image shows the presence of the solvent and stabilizers, oleamine and oleic acid on the nanoparticle surface. We can observe their functional groups. Dynamic light scattering show a estimated particle size distribution. The iron phosphide nanoparticles have an estimated size between 40 and 50 nanometers, while those of nickel phosphide of approximately 100 nanometers. Transmission electron microscopy image shows a quasi-spherical morphology of the iron phosphide nanoparticles and an approximated particle size of 50 nanometers. It is important to mention that the particle size distribution analyzed by DLS is larger compared to results obtained by TEM. This is due to the presence of the oleamine and oleic acid on the iron phosphide nanoparticle source. Currently, the acid hydrolysis reaction of sargassum and the analysis of the reaction products are in process. As you can see, sargassum undergoes a pretreatment. For first the recollection, second the wash, third the dry off, and finally grind. The acid hydrolysis reaction are carried out in a per-instrument reactor. We add 10 grams of sargassum, 100 milliliters of water, iron phosphide or nickel phosphide nanoparticles, and finally 3 milliliters of phosphotunsic acid. The reaction conditions are temperature 200 degrees, time 2 hours, and finally stir 600 revolutions per minute. Reaction conditions were favorable to obtain iron phosphide and nickel phosphide nanoparticles. FTIR spectrum showed the stabilization of nanoparticles by the interaction between the polymer on its surface. DLS analysis estimated the size of particle. Iron phosphide nanoparticles are smaller than nickel phosphide nanoparticles. This might be due to the difference in synthesis times. The image of iron phosphide nanoparticles shows the size after several purification times is smaller than the LSA image due to polymer removal from the nanoparticle surface. The quasi-spherical morphology was observed too.